Myself, Dr. Hanuman Prasad. I am working as an assistant professor at the chemistry department in IARE. Today I am discussing a topic entitled potable water and its specifications. The contents involved in this topic are introduction to potable water, specifications of potable water according to Bureau of Indian Standards, which is abbreviated as BIS. Steps involved in treatment of water such as screening, sedimentation, coagulation, filtration and disinfection. These are the contents I am going to discuss in this topic. The first content is introduction to potable water. As you all know that potable water is nothing but drinking water. The water which is used for drinking without having any kind of hardness causing or salinity causing or microorganisms in water. So, in order to drink water, the water should have certain permissible limits of the certain things. Those permissible limits of certain things are: number 1, hardness causing substances; number 2, salinity causing substances; number 3, microorganisms. In fact, the potable water must have permissible amounts of hardness causing substances and permissible amounts of salinity causing substances, and potable water must be free from microorganisms, because microorganisms are not at all allowed in potable water because these are responsible for various diseases. So that is why microorganisms are not at all suggested in drinking water. This is about the introduction of potable water. Let's go to the next content. Specifications of potable water according to Bureau of Indian Standards, BIS. The common parameters to specify the water are color, taste and odor. And firstly, these specifications are given by Indian Standards and code is 10500/2012. This is the code which is set as standard specification for potable water. And the organization which sets these specifications for potable water is Bureau of Indian Standards, which is abbreviated as BIS. The first specification is color, which is measured in units of either TCU or HU. The full form of TCU is True Color Unit, and that of HU is Hazen units. The permissible limit of color is up to 25 Hazen units, and the desirable limit is only 5 Hazen units. Means the permissible limit indicates if there are no water purification techniques available surrounding us, we can permit it up to 25 ppm. It is the maximum limit which we can permit for drinking. But beyond this, the water is not at all safe for drinking. And especially the desirable limit is only 5 Hazen units per color. The second parameter is taste as well as odor, which is measured in units of TON. Full form is Threshold Odor Number. The desirable limit for taste and odor is 1 TON and permissible limit is 3 TON. So desirable limit is only 1 TON, but we can permit up to 3 TON. The next parameter is turbidity, which is measured in units of NTU. Full form is Nephelometric Turbidity Unit. The desirable limit is 1 NTU and the permissible limit is 5 NTU. the required limit is only 1 NTU and it can be relaxed up to 5 NTU. But beyond 5 NTU, the water is not suitable for drinking. The next parameter is TDS. Full form is total dissolved solids, which is measured in units of milligram per liter or ppm. Milligram per liter is nothing but ppm, parts per million, which is same as milligram per liter, mg per L. The desirable limit for TDS is 500 ppm and the permissible limit is 2000 ppm. Beyond 2000 ppm, the water is not safe for drinking and the required limit is only up to 500 ppm. And beyond that, beyond 2000, we cannot drink. And 2000 is also maximum limit which we can permit for drinking. That doesn't mean that we always have to take water with 2000 ppm of TDS. I hope you understand. The desirable limit is only 500 ppm. But when there are no techniques available surrounding us for purification, we can relax it up to 2000 ppm. The next parameter is pH. pH for specification water having desirable limit of 6.5 to 8.5 and the permissible limit is same, which means that there is no relaxation for pH. So 6.5 to 8.5 is the desirable as well as permissible limit of pH for drinking water. And the next parameter is hardness, which is measured in units of milligram per liter of CaCO3. I have already mentioned why the hardness of water is mentioned in terms of CaCO3 because of two reasons. The first reason is CaCO3 is highly insoluble in water, so easily we can measure the hardness in terms of CaCO3. And the second reason is the molecular weight of CaCO3 is 100 and its equivalent weight is 50, which are round figures. So easy for the calculations of hardness. That is why CaCO3 terms are preferred for measuring hardness. The desirable limit of hardness is 200 ppm and the permissible limit is 600 ppm. But the desirable limit is only 200 ppm. Beyond that, it is not suggested, but when there are no techniques available surrounding us for purification, we can relax up to 600 ppm. But beyond 600, it is not suggested for drinking. Next parameter is alkalinity. Alkalinity is also measured in units of milligram per liter of calcium carbonate, same as hardness, which has desirable limit of 200 ppm, which is also same as hardness, and permissible limit of 600 ppm, same as hardness. Desirable limit of hardness as well as alkalinity is 200 ppm in terms of CaCO3. And the permissible limit of hardness as well as alkalinity is 600. The next parameter is fluoride content, which is measured in units of ppm or milligram per liter. The desirable limit of fluoride content in drinking water is 1 ppm and it can be relaxed up to 1.5 ppm, which means that the permissible limit of fluoride content is 1.5 ppm. But note that the desirable limit is only 1 ppm. So beyond 1.5 ppm, the water is not at all safe for drinking. The next parameter is chloride content, which is also measured in units of ppm and the desirable limit is 250 ppm, whereas permissible limit is 1000 ppm. Beyond 1000 ppm, the water is not at all safe for drinking. 250 ppm is the one that is desirable limit. But no techniques are available surrounding us, let's say, then in that case, it can be relaxed up to 1000 ppm in case of chloride content. The next parameter is nitrate content, which is also measured in units of ppm or milligram per liter The desirable limit of nitrate is 45 ppm and there is no relaxation for nitrate content. So the permissible limit is also 45 ppm. There is no relaxation for nitrate content, which means that the permissible limit is also 45 ppm for nitrate content. The next parameter is sulfate content, which is also measured in units of ppm or milligram per liter. The desirable limit is 200 ppm and the permissible limit is 400 ppm. The desirable limit of sulfate content in drinking water is 200 ppm and the permissible limit is 400 ppm. Beyond that, we cannot drink water. Next content is calcium, which is measured in units of ppm or milligram per liter. The desirable limit is 75 ppm and permissible limit is 200 ppm. Beyond 200 ppm, the water is not safe for drinking. The next parameter is iron, which is measured in units of ppm and its desirable limit is 1 ppm, which cannot be permitted more than 1 ppm. So there is no relaxation, which means that the permissible limit is also 1 ppm for iron content in drinking water. The next content is copper content. The desirable limit of copper content is 0.05 ppm and its permissible limit is 1.5 ppm. Beyond 1.5 ppm of copper content in water is not safe for drinking. So the permissible limit is 1.5 ppm and the desirable limit is 0.05 ppm for copper content in drinking water or potable water. Finally, microorganisms such as E. coli. E. coli is abbreviated as Escherichia coli, which is measured in units of CFU, whose full form is column forming unit, which means that the bacteria or microorganisms form a column kind of thing. So how many column forming units are there? In such units, we measure the microorganisms such as E. coli. Full form is Escherichia coli. And these are very dangerous if present in drinking water. They cause various diseases. So it is not at all allowed in drinking water. So the desirable limit is 0 CFU and the permissible limit is also 0 CFU. So microorganisms should not be present in potable water. That means water must be free from E. coli, microorganisms. Okay, then only the water is potable. Let's go to the next content. The steps involved in treatment of water. So for water to be drinking, there are some steps to get treated. There are 5 steps. First one is screening. Second one is sedimentation. Third one is coagulation. Fourth one is filtration. Fifth one is disinfection. Let's look at each one individually. The first step in the treatment of water is screening. Screening is defined as the process of removal of floating matter from water with the help of a screen. The screen is the one which have a large number of holes. When raw water is passed through a screen which contains large number of holes, then the floating matter present in raw water will be trapped in the holes present in screen. That is how the floating matter like wood pieces, leaves, etc. can be trapped in the holes of screen. And by passing through screen, the water will be free from floating materials such as wood pieces, leaves, etc. And using screening technique, only floating matter can be removed. but not other impurities like suspended impurities, colloidal impurities cannot be removed by screening technique. Screening technique is only for the removal of floating materials such as wood pieces and leaves, etc. So for the purpose of screening, we have to take a screen and the raw water should be passed through it, which contains holes, and the floating material will be trapped in the holes. That is the mechanism involved in screening process. Let's go to the next step, which is sedimentation. Sedimentation is nothing but the process of removal of suspended impurities from water with the help from water by allowing to stand for 2 to 6 hours in big tanks. Sedimentation is nothing but the process of removal of suspended impurities from water by allowing to stand for 2 to 6 hours in big tanks. So the water must be allowed to stand. Stand means the water must be allowed to settle for at least 2 hours, maximum 6 hours. That is depending on the nature of suspended impurities. So in between 2 to 6 hours, we will optimize the time for allowing the water to settle at the bottom of the big tanks, because this sedimentation is carried out in big tanks or large tanks. So what is the principle involved in the settling of suspended impurities at the bottom of large tanks? The principle is gravitational force of attraction. Due to gravitational force of attraction, the suspended impurities are settled at the bottom of the big tanks and it can be free from suspended impurities. So sedimentation technique works in such a way. And mainly sedimentation process removes only 70 to 75% of suspended impurities. Means the efficiency of sedimentation process is only 70 to 75%, which means that even after sedimentation, there will be still 25 to 30% of suspended impurities present in water. And in addition to suspended impurities, there will also be colloidal impurities, which cannot be removed using sedimentation process. And for the removal of rest of the suspended impurities as well as colloidal impurities, there are other techniques. Now we are going to discuss the technique. The technique is called coagulation. Coagulation is defined as the process of removal of colloidal impurities from water by converting into precipitate with the help of a coagulant. And coagulant is a substance or chemical which is added to water to convert colloidal impurities into precipitates. Okay. So coagulation is the process of removal of colloidal impurities from water by converting into precipitate with the help of coagulants. Coagulant is a chemical or substance which is used to convert colloidal impurities into precipitates with the help of the substance, means with the help of coagulant. So the examples of coagulants are alum, which is chemically called sodium aluminate. Its formula is NaAlO2. The formula of alum is NaAlO2. Chemically it is called sodium aluminate. And there is one more coagulant which is aluminium sulfate, which is formulated as Al2SO4 thrice. And mainly what are the examples of colloidal impurities? They include finely divided silica, clay, etc. So coagulation is the technique in which the colloidal impurities are converted into precipitates with the help of a coagulant. And coagulant is a chemical or substance which converts colloidal impurities into precipitates. The examples of colloidal impurities are finely divided silica, means small particles of silica, clay, etc. And the examples of coagulants are alum, sodium aluminate, formula is NaLO2, and aluminium sulfate, Al2SO4 thrice. What happens when alum is added to water? How it will convert colloidal impurities into precipitates? Let's see with an equation. Here alum is added to water. When it reacts with water containing colloidal impurities, it will convert into NaOH and AlOH thrice. And AlOH thrice is the precipitate in this case, which is a gelatinous white precipitate, means jelly kind of precipitate which is having white color. And there is also NaOH formed in this reaction, which converts the hardness causing substances, especially permanent hardness causing substances, especially magnesium chloride, magnesium sulfate, into magnesium hydroxide, which is also a precipitate. Let's look at that equation. When the permanent hardness causing substance such as magnesium chloride or magnesium sulfate reacts with NaOH, which is formed in the coagulation technique, when NaLO2 is added to water, in that case NaOH is formed, that will react with permanent hardness causing salts and converts into the precipitate, magnesium hydroxide. Along with this, NaCl will be formed to balance the equation. 2 NaOH must be there. So MgOH twice will also be getted from water. Means permanent hardness causing substances can also be getted from water. And NaCl is a salinity causing substance which can be removed by other techniques, which is called desalination. The technique for desalination is reverse osmosis, RO process. So that is how coagulation works, which converts colloidal impurities into precipitates with the help of a coagulant. The equation is shown here. When NaLO2, which is a coagulant, is added to water containing colloidal impurities, the colloidal impurities are converted into precipitates in the form of aluminum hydroxide, which is a gelatinous white precipitate. And NaOH is also formed in this reaction, which converts permanent hardness causing salts such as magnesium chloride and magnesium sulfate into magnesium hydroxide, which is a precipitate, so which will be getted easily from water. And the next technique is filtration. Let's look at the filtration process. First of all, filtration is defined as the process of removal of fine suspended particles, unwanted color and unpleasant taste as well as odor, and certain microorganisms by passing through a bed of fine sand and other granular materials. So, filtration is defined as the process of removal of fine suspended particles, means small suspended particles, unwanted color, unpleasant taste and odor, and certain microorganisms by passing through a bed of fine sand and other granular materials. Okay. So, there are two things required in this filtration process. One is the device to carry out filtration. The name of the device to carry out filtration is filter. The name of the device to carry out filtration is filter. One of the examples of filter is slow sand filter. The example of a filter is slow sand filter. And the second thing required in this filtration process is filtration medium. Filtration medium, which is the porous material used in the filtration process. The porous material used in the filtration process is called filtration medium. And the device used for filtration is called filter. The example of a filter is slow sand filter, and the example of a filtration medium is silica, which has a chemical formula of SiO2. Let's look at the working condition of slow sand filter. Slow sand filter contains of 4 layers. One is fine sand layer, which is a layer of small sand particles, and below that there is coarse sand layer, which is a layer of big sand particles or large sand particles, and below that there is fine gravel layer, which is a layer of small gravel particles. And below that, there is a coarse gravel layer, which means a layer of large gravel particles. So in this technique, first of all, water is passed into the filter from this side. Which water is passed here? Raw water. So this is all water, and it will be passed through all these four layers. First through fine sand layer, next through coarse sand layer, next through fine gravel layer, and finally through coarse gravel layer. By passing through all these layers, several impurities such as I mentioned, fine suspended particles, unwanted color, unpleasant taste as well as odor, and certain microorganisms can also be removed in this filtration process. And finally, the water is collected from here, which is pure water, you can say. It may not be potable, but it is a pure water, means compared to raw water. Compared to raw water, this is pure water. Okay, so this is the working of a slow sand filter, and in this there is a use of filtration medium, which is a porous material. The filtration medium in this case is 4 filtration mediums are there. Four filtration media are present here. One is fine sand layer, second one is coarse sand layer, third one is fine gravel layer, fourth one is coarse gravel layer. And the next technique is disinfection. Means in this process, certain microorganisms can be removed, but most of the microorganisms are still present in water, which can be removed by disinfection process. Let's look at that. Disinfection is nothing but the process of destroying or killing or removing microorganisms, disease producing bacteria, means pathogenic bacteria. Pathogenic, the term means, patho means disease, genic means causing, bacteria means microorganisms. So pathogenic bacteria are nothing but disease causing bacteria. So in disinfection process, they will be removed or destroyed, or they will be killed. Okay, so that the process of disinfection is to get potable water. Finally, we will get water safe for drinking, which is nothing but potable water. So disinfection is the process of removal or destroying or killing of pathogenic bacteria, means disease causing bacteria present in water, to make the water potable, means to make the water drinking. And the chemicals or substances used for this process are called disinfectants. The chemicals or substances used for this disinfection process are called disinfectants. The disinfection of water can be carried by the following techniques, which are mentioned here. First one is boiling. In boiling technique, the disinfectant is heat itself. In boiling technique, disinfectant is heat. So when water containing microorganisms is heated, the microorganism activity will be destroyed. That means microorganisms will be killed. So in this boiling process, heat is the disinfectant. And next technique for disinfection is by using UV light. So in this case, UV light itself is the disinfectant. When UV light is passed through water containing microorganisms, then those microorganisms which will respond to UV light can be destroyed, such as certain microorganisms. So definitely they will respond to UV light and they will be killed by UV light. So UV light will act as a disinfectant. And the next technique is ozonization. In the process of ozonization, which is one of the disinfection processes, the disinfectant will be ozone. Disinfectant is ozone. But in fact, ozone is not the final disinfectant. Ozone is the initial substance which we will add to water and it will convert into nascent oxygen. O3 will be dissociated into molecular oxygen as well as nascent oxygen. This is called nascent oxygen. Nascent oxygen is nothing but the freshly produced or newly generated oxygen and which is acting as disinfectant. Means it is responsible for destroying of bacteria present in water in ozonization process. And such nascent oxygen is generated from ozone by dissociating into molecular oxygen as well as nascent oxygen. Nascent oxygen is nothing but freshly generated or newly produced oxygen which will destroy the bacteria. And there are these three techniques which are used in chlorination process. In chlorination process, one of the techniques is using bleaching powder. So bleaching powder is added to water and water will be free from microorganisms which will respond to bleaching powder. The technique involved in this process is bleaching powder CaOCl2 which is chemically called calcium oxychloride. It is the chemical name of bleaching powder and CaOCl2 is the chemical formula of bleaching powder. It will react with water containing microorganisms and it will convert into calcium hydroxide as well as chlorine gas. Now chlorine gas is generated in between the process. It is not taken directly. Keep a note of it. Why I am mentioning this is chlorine gas is toxic gas. So this chlorine gas will react with water containing microorganisms and it will produce HCl as well as HOCl. HOCl is the actual disinfectant in this process. Not only in bleaching powder or chloramines or chlorine, in all these chlorination processes. Okay. So initially bleaching powder such as calcium oxychloride is added to water containing microorganisms. It will convert into calcium hydroxide as well as chlorine gas. Here chlorine gas is generated in between the process which will further react with water and converts into HCl as well as HOCl. You know that HCl name is hydrogen chloride or hydrochloric acid and HOCl is hypochlorous acid. What is HOCl? Hypochlorous acid. It is the actual disinfectant in this process. In all these processes, the actual disinfectant is HOCl. So, how HOCl will deactivate or destroy the bacteria? I am telling little mechanism. So, please pay attention. Hypochlorous acid goes and fits in the active site of enzymes present in the proteins of microorganisms and in the active sites it will dissociate into H plus and OCl minus. In the active site of enzyme it will dissociate into H plus and OCl minus. When it dissociates in the active site of enzyme of proteins of bacteria, which means that the enzyme is destroyed. When enzyme is destroyed, protein will be destroyed. As a result, the microorganism activity will be destroyed. As a result, it will be killed. That is how the removal of microorganisms using HOCl will occur. And HOCl is the disinfectant which will generate in the chlorination processes. Here I am discussing about calcium oxychloride or bleaching powder technique. Okay. And next chlorination technique is by using chloramines. When chloramine is added to water, such as NH2Cl is the chemical formula of chloramine, it will react with water and produces NH3 as well as HOCl. As I told, in all these chlorination processes, HOCl, hypochlorous acid, is the disinfectant which will destroy the bacteria by fitting in the active site of enzyme present in the proteins of microorganisms, and it will dissociate into H plus and OCl minus ions, and it will destroy the enzyme. As a result, the microorganism will be destroyed. As a result, the water will be free from the microorganisms which respond to HOCl. And the next chlorination technique is by using direct chlorine gas. By using direct chlorine gas. This is little cautious, not little cautious, lot of precaution must be taken here. Because chlorine gas is toxic, if it is taken in excess, that will further cause several problems. Even excess of chlorine may cause death of human beings. So, care must be taken while using direct chlorine gas, because excess chlorine will cause even death. So, chlorine gas handling must be taken in presence of experts. As I have shown here, chlorine gas reacts with water and generates HCl as well as HOCl. HOCl is the actual disinfectant. I have mentioned already here. In all these chlorination processes, HOCl is the actual disinfectant. Once again, I am repeating how it will destroy the microorganisms. HOCl goes and fits in the enzymes. In the enzymes, there will be binding sites. HOCl fits in the binding sites present in the enzymes of proteins of microorganisms, and it will dissociate into H plus and OCl minus ions. As a result, the active site will be deactivated, and hence the microorganism will be destroyed. That is how water will be free from microorganisms, by using this chlorination process. And by using all these processes, whatever I have mentioned here, screening process, sedimentation process, coagulation process, filtration process, and disinfection process. By using all these processes, water will be free from several impurities such as hardness causing impurities, salinity causing impurities, and microorganisms. As a result, the water will be potable. So this is what is about various techniques involved in screening, various techniques involved in treatment of water. Why to do all these process means treatment of water? To get potable water. And BIS has given these kind of specifications for drinking water. So in order to get all these specifications, we need to treat water such as screening, sedimentation, coagulation, filtration, disinfection. And the salts can be removed from water by using desalination process, as I have already mentioned. The example of desalination process is reverse osmosis. Reverse osmosis is the process in which the water will be flown from high concentrated solution to low concentrated solution with the help of a semi-permeable membrane. In this case, the high concentrated water will be coming as low concentrated water. Means the salts will be gathered from water by passing through a semi-permeable membrane, which is the membrane used in reverse osmosis process. And reverse osmosis process is the technique for desalination of water. Thank you very much for your patience.
Like, share and subscribe. Hit the bell icon for more updates.